Hey guys, we're going to work towards getting to the end of chapter 5, and in this lecture we're going to talk about something called the Carnot Cycle. The Carnot Cycle is kind of a theoretical cycle, and we basically use it to see how efficient an engine could be. It involves a system that undergoes a series of 4 internally reversible processes. Remember, reversible, that's like the optimal case you can have, and actual processes are typically irreversible, so this is kind of a theoretical case. Now, we said we had 4 processes. 2 of those processes are adiabatic, and the other 2 are going to be isothermal. Now, let's review. Do y'all remember what these mean? Hopefully you do, but if not, adiabatic means no heat transfer. So Q would be 0. Isothermal means temperature is constant. All right, so we've got those 2 requirements there. Now we're going to go through and we'll talk about the 4 processes, and we're going to draw them on a PV diagram. So let's go ahead and get this diagram set up. Here's V, here is P. Alright, and what we're going to do is we're going to have 2 lines. These are going to be isotherms, so they're constant temperature. This one let's call TH. This one, let's call that TC. And as we go through the different processes, we'll label the states and everything on this diagram. Just know that these 2 lines are isotherms, so at any point on these lines, your temperature is going to be TH or TC, depending on which line you're on. Now, process 1, 2. This part of the Carnot cycle, this is going to be a compression with no heat transfer. So that's what's going to happen in this process, going from state 1 to 2. Now, if we've got compression, what do we think is going to happen with the pressure? That's right. So pressure is going to go up. So pressure goes up, and even though we don't have any heat transfer, our temperature goes up. Now, if we draw that on our PV diagram, let's put 1 over here. So we're originally at this pressure, this specific volume. Now we're going to end up at state 2, so that's going to be over here. Alright, so our pressure is going to go up, and then our temperature goes up to TH. So that'll be the first process. Now after we get to state 2, we want to get to state 3. The process we need for that is that we will allow for heat transfer from the hot reservoir while keeping the temperature constant Now what's going to happen here, we're allowing energy to come in from our hot reservoir, but we're going to keep that temperature constant. Now that means that the expansion is going to have to allow the temperature to stay constant. All right, because something has to happen here if we're going to keep the temperature constant. You can't keep the temperature constant and then not have expansion. That expansion has to happen. And then if we allow this expansion, our pressure is then going to decrease. Now remember, we're keeping temperature constant. So here from 2, we're going to stay on this TH line, and we're going to come down to 3. So that'll be that process. Now we need to get to state 4. So our next one, we will have our gas. It's going to continue to expand without heat transfer until TC is reached. Okay, so what we're trying to do here is we're trying to get down to TC. Let's label that as 4. So we'll just have a line, looks like that. Now again, we don't have any heat transfer. We're just allowing the gas to expand until we lower that temperature to TC. Okay. In the process, you can see the pressure is going to change because you're allowing the expansion. So pressure drops, we reduce our temperature, and then last thing we need is the process that goes from 4 back to 1. In this one, the gas is going to be compressed isothermally, so temperature is constant. That means we must lose energy through heat transfer and the way that happens is we're going to discharge energy to the cold reservoir. Okay, so we're getting rid of energy, we're sending it to the cold reservoir, and we're going to have compression until we get back to our original pressure that we had at state 1. So we'll compress until we reach P1. So then if you go back to the drawing, you just go from 4 back to 1. So that's kind of what it looks like on the PV diagram. Now notice, we said we had 2 adiabatic and 2 isothermal processes. So you can see process 1, 2, this was no heat transfer, so this one is adiabatic. Or actually this one, I'm pointing to the wrong one. So that's adiabatic. The other one with no heat transfer is 3, 4. So this one is adiabatic. And then the other 2 are constant temperature, and you can see that because they go on the isotherms. So let's just put isothermal and then isothermal. Now that's kind of what that cycle looks like. All right. Now, since that might not be overly explanatory, let's look at an application of this kind of cycle. And then maybe you'll be able to kind of imagine better what we're talking about here. So let's look at this next page here. Let's draw a picture to start out with. We're going to have a hot reservoir. And below that, let's draw this system. Okay, so we got a system here, and this system, let's say we've got a boiler here. All right, so we've got this boiler, and we're going to have energy transfer by heat from the hot reservoir into this boiler. That's going to be QH. Okay. Now, from the boiler, let's go down to a turbine. Okay, so here's a turbine, and this turbine's going to produce work. All right, so it could power something else, for example. And then after that, we flow out of that turbine, and then we are going to come into a condenser. So now we'll have this. We flow through the condenser, and then down here, we've got our cold reservoir. Now at the condenser, we're going to discharge energy in the form of heat to the cold reservoir. That'll be QC. After we do that, we come out of the condenser, and then we're going to come up through here, and this is going to be a pump. And remember, a pump has to have energy supplied, so we'll put work going into the pump, and after the pump we flow to the boiler. Okay, so this is going to be an application of the Carnot cycle. Now let's go through and we'll draw on the PV diagram each of the processes as they happen, and we'll kind of explain what's going on. All right. Okay, so first, let's start up here. Let's say this is state 1 right here as we come out of the boiler. Let's just start with that. And let's see. Let's put this one right here, so hopefully I have enough room. We're going to say that water flows through the boiler. So as it flows through the boiler, we're going to have liquid water. It turns to vapor. So let's just put liquid to vapor at a constant temperature TH. So that's what's going to happen as the water flows through the boiler. Okay, so the boiler is going to vaporize that liquid water, and that temperature is going to be held constant at TH. So if we put this on the PV diagram, this is going to be a small diagram here. You got that. We're going to have our isotherm, which looks like this. That line indicates TH. So now what we're going to do when we get to state 1, we're going to be over here, right? Because we're going to have all vapor. So we're at state 1, and you'll see in a minute when we talk about state 4 that when we come into the boiler here, or when we leave the pump, we're going to be at state 4, which is over here. So you might want to put that on it. We'll talk about this point in just a second. All right, so this is the process that the boiler takes care of. Does boiling, creates vapor, vaporizes that water. Now next, after the water or the vapor comes out of the boiler, we're going to send it through a turbine. So at that point, we've got steam. We're going to say steam expands adiabatically. So that means no heat transfer. And that's done in the turbine. Remember, the turbines work because you have fluid passing over those blades. It turns the blades, and work is developed. All right, so we got work developed. Now, as all this is happening, our temperature decreases to TC as the pressure decreases. All right, so now we have that. Let's draw our PV diagram again. So we're going to come up like this. Let's draw our TH line. This is the one we had up here. We're at 1 right here. Remember, this was 4. We'll talk about that one in a second. So we're going from 4 to 1 up here on TH. Now, for this one, we're going to TC. So that's going to be at a lower temperature. So let's draw the line below there. And now we're going to state 2. So here, let's put state 2. So right there. All right, so our temperature is decreasing, our pressure is decreasing, work's being developed. That's what's happening right here. Now, after that, we are going to go through the condenser. So we still have steam at this point right here. So now we can say that steam enters a condenser. And now what happens is we're going to have heat transfer to a cold reservoir. So basically we're trying to get rid of energy here. We're going to send it to the cold reservoir. We're going to discharge it. Now as we do that, some of this steam or vapor that we have is going to condense because we're removing that heat energy. Let's put some vapor condenses. let's see, at a constant Tc. Now we're saying constant Tc, so we're having an isothermal process here, so we're going to stay on this Tc line, and we're going to come over here. Let's just say we go there, because we just said some of the vapor is going to condense. We didn't say all of it, so we're not going to go all the way over to the saturated liquid point. Now we're here, that's going to be 3, that was 2. Actually, I'm getting ahead of myself. Let's draw a new diagram, I forgot. It'll make more sense that way. Put our TH line, put the TC line, and let's redraw what we had. We went from 4 to 1, then down to 2. Now we have an isothermal process. Let's go over to 3. So this is what happens right here for this process. And now the last thing we need to do, we need to get back to state 4. So now we've got this condenser. What comes out of the condenser is then going to go through this pump. Now work is supplied to that pump, so the pump's able to run. We have an energy supply there. And what the pump does is it takes in that liquid vapor mixture, so our liquid vapor mixture goes to the pump. You could also call it a compressor. And what that pump is going to do is it's going to return the liquid vapor mixture all the way back to the liquid state. So let's just put returns it to the liquid state, and then once that water is all in the liquid state again, it's ready to go back through the boiler. Okay, now if we draw that one on one of these PV diagrams again. Let's put everything back on here. So we got TH, you got TC, and then label your states. Now we're going to go back up that way. Okay, so that's what it's going to look like. And that kind of gives you an idea of what we have going on during a Carnot cycle. So the important thing to realize is we've got the 2 adiabatic cycles and then the 2 isothermal cycles. All right, so that's what it's going to look like. All right. And I know this video is getting kind of long, but let's talk about one more thing before we move on. Let's talk about the thermal efficiency here. When we're talking about the Carnot cycle. For the thermal efficiency, our eta max is going to be 1 minus Tc over Th. All right, so similar to what we had before. Now the reverse Carnot cycle, that's going to be the Carnot refrigeration and heat pump cycles. In this case, the magnitudes of our energy transfers are going to be the same, but the energy transfers will be in the opposite direction. So just similar to what we had with the other refrigeration and heat pump cycles. Now we also have equations to look at the performance of this cycle. So for refrigeration, we're going to have beta max is going to be Tc over Th minus Tc. And then for the heat pump cycle, we're going to have gamma max. That'll be Th over Th, whoops, minus Tc. All right, so there you go. That's about the Carnot cycle. I will see you guys in the next video.